So we now look at entire functions as we still talk about analytic functions. We have seen holomorphic functions, harmonic functions, and now we are considering entire functions under the broad concept of analytic functions like that. So let's go ahead and see what an entire function is. By definition, an entire function is a function that is analytic or holomorphic at every point in the complex plane C. So we've seen all of that previously. This means it is differentiable everywhere in the complex plane, and it has a power series expansion valid for all z belonging to the complex plane. So talking about the power series characterization, a function f of z is entire if it can be written as f of z equals summation from n equals 0 to infinity of a sub n z raised to power n, with radius of convergence equal to infinity. Okay, that's when you say a function is entire. So straight up, we have examples. Any polynomial f of z, which is a naught plus a1z plus a2z squared plus all of that up to a n z raised power n is entire. This is like a polynomial thing. So it's more like a corollary for everywhere differentiability, like the fact that it can be differentiable everywhere, and that is true for polynomials. So an example of that would be f of z equals 3z cubed minus 2z plus 1. And the reason is finite sums of analytic functions remain analytic everywhere. So as far as you can express any number as a finite sum, then you can be sure it is analytic everywhere. So we have another example talking about exponential function. So the exponential function is defined as e raised power z equals summation from n equals 0 to infinity of z over z power n over n factorial. So this series converges for all z in the complex plane. Therefore, e raised power z is said to be an entire function. That's another example. Example 3 is about trigonometric functions. The sine and cosine functions are entire in that sine z is equal to summation from n equals 0 to infinity of e raised power minus 1 raised power n z raised power 2n plus 1 over 2n plus 1 factorial. And cos z is summation from n equals 0 to infinity for minus 1 raised power n z raised power 2n all over 2n factorial. Of course, sine z is an odd function, whereas cos z is an even function. So, can we give examples of non-entire functions and having seen examples of entire functions? So, the following are not entire. F of z equals 1 over z. That's the inversion of the complex number z. And because it's not defined at z equals 0, when x is 0 and y is 0, then this function is not defined. And that's what it means for z to be 0. Then number 2, f of z equals 1 over z squared plus 1. It has singularities at z equals I and minus I, right? Like that, what we mean by that is this. If you have z squared plus 1. That's z squared plus 1 there. You have z squared plus 1 equals 0. If you equate this to 0, that means z squared equals minus 1. So, and that means you have z squared equals plus or minus square root of minus 1. So, yeah, z squared is gone. If you take square root of both sides, so z now is plus or minus I. Square root of minus 1 is I. So it has singularities at plus I and minus I, and that is why it is not an entire function. So, and then 3, f of z equals log z. So it is not analytic everywhere because there's a branch cut. So if you try to visualize it using, okay, maybe I'm trying to, maybe, I don't know if let me try to see if I can use Desmos to describe some of these ones, right? So like having one of z, I can use that for one of x. So you can see that it is asymptotic around 0, so it's never getting to 0. So that's why it's not defined there. So if I take that away and I talk about 1 over z squared plus 2, 1 divided by z squared plus 1 rather, plus z squared plus 1, like this. Oh, okay, I can't use z. I have to still use x. Yeah, x is what it recognizes. Okay, I think there's a subscript there that should not be there. Yeah, is it good now? Okay, that's still a problem. Okay, x raised to power 2. Yes. So you see again that Well, this is so you can see there's a kind of jump around this place or so. But maybe this does not really tell the story because in the complex plane now we have jumps at -1 and +1 like that. Yeah. Then we have log z, of course, log. Let's try log x and see what it may not really capture the picture. Okay, log x. Okay, we have log x there. So it's not defined for negative values. You can't find it for negative values like that. So it's not analytic everywhere because there's a branch cut there. Negative values are not allowed. Okay, so let's talk about properties of entire functions. If f and g are entire, then f plus g is entire. So that means the sum of two entire functions is entire. Then f dot g is entire. That means the product of two entire functions is entire. And f of g of z is entire. That means the composition of two entire functions is also entire. Example, f of z equals e raised power z plus z squared is entire because both terms are entire. So that means e raised power 2z is entire and z squared is entire. So their sum is also entire. If you also multiply them, it will be entire too. Then we have the Liouville's theorem. If an entire function is bounded, then it must be constant. That is, if the absolute value of f of z is less than or equal to m for all z in the complex plane, then we can say that f of z is actually constant. Okay, so every bounded entire function is constant. So, or we can also say every, okay, I don't want to overstretch it. Let me just leave it there safely. Okay, fundamental theorem of algebra. We consider this under polynomial function, polynomial equations. We're talking about fundamental theorem of algebra that every polynomial has at least every non-zero polynomial, every non-constant polynomial has at least one complex root. So every non-constant polynomial has at least one complex root. This follows from Liouville's theorem. So if the polynomial is of degree 3, it has uh, at least it has three solutions, maybe all complex or some complex and some real or all real, whatever. Talking about if you look at complex numbers as the biggest umbrella for numbers, right? Then every polynomial has the number of roots equal to its degree. So this follows from the Liouville's theorem. And then we talk about the growth of entire functions. How do entire functions grow? So entire functions can grow at different rates. We describe growth using the absolute value of f of z following e raised power absolute value of z raised power p, right? Raised power rho. So if rho is equal to 0, of course, this whole thing is going to be 1. So anything raised power 0 is 1. So we have e raised power 1. So we have a polynomial in that case. But if rho is equal to 1, it will be exponential in that regard. Then if rho is greater than 1, then we have a faster growth like that. So if you have an example, this worked example now, if you want to show that f of z is e raised by 2z plus 3z squared is entire, solution, we see that e raised power 2z is entire, right? Because it is differentiable everywhere, right? Then z squared is a polynomial, which is also entire. And sum of entire functions is entire. Therefore, f of z is entire, basically. And then example 2, you want to determine whether f of z equals e raised power z over z minus 1 is entire. First of all, e raised power z is entire. But the denominator is 0 at z equals 1. So when z is 1, this denominator will be 0, and that makes the whole function undefined. Therefore, f of z is not entire because it has a pole at z equals 1. So a pole is like a point of discontinuity. As far as that exists, you can also see the function is entire. Okay, so we go on to talk about we have a Python code here for exponential approximation, right? So we just have z raised power n factorial, so which approximates the exponential function, and you see it growing out like that. And you see the approximate value is 1.68 something something plus 2.2 something in the complex part. So you see the exact is also very close to it, almost to to a very large number of decimal places, both for the imagine real part and the imaginary parts. Then we have polynomial versus exponential now. So the polynomial is x cubed, that's blue, and then the exponential is e raised to power x, which is orange. So you see all of that there. So that's also an approximation for those two right there. So we can do the approximation. In summary, we say that entire functions are analytic everywhere in C. That is, they are differentiable anywhere, everywhere rather, in the complex domain. Then examples include polynomials, exponential functions like e raised power z, and trigonometric functions like sine z and cos z. They are closed under addition, multiplication, and composition. That means if you add, multiply, or compose two polynomials, you get a polynomial. If you add, multiply, or compose two exponential functions, you get an exponential function. If you add, multiply, or compose two trig functions, you get a trig function, and they are entire. So Lewis' theorem restricts bounded entire functions. So we have practice problems as usual. You have 1 to 10 there, and you have 11 to 20 right there. So as usual, I'm going to solve two of them as we bring this to a close. Um, so uh, I'll I'll choose two to solve, and then we keep it moving. So problem six, I'm going to solve problem six to show that f of z equals e raised by z squared is entire. Then I also want to solve 16, which to determine whether f of z sine z over z is entire and justify the answer. So let's go to the worksheet and have that done. So starting from problem six. So now we have problem six, and it is to show that f of z equals e raised by z squared is entire, is entire. So uh we know we know that the exponential function has the power series, e raised by w, e raised by w equals summation from n equals 0 to infinity w over w power n over n factorial. So, and we substitute w equals z squared. So in that case, we have e raised by z squared equals summation from n equals 0 to infinity of w is z squared, right? So that's z squared all over z squared power n all over n factorial. So if that is the case, that means we have summation from n equals 0 to infinity of z raised by 2n all over n factorial. So we see basically that this is a power series. This is a power series in Z with infinite radius of convergence. So if you compare this with the power series, we know that's basically it. With infinite radius of convergence. So with that settled, we can say therefore, e raised by z squared is analytic for all z which belongs to the complex domain. Hence, f of z equals e raised by z squared is entire. So that settles that. And move on to problem 16. So for problem 16 now, so we want to determine whether f of z equals sine z all over z is entire. Okay. So we have that. So we use the series expansion, of sine z, which is that sine z is equal to summation from n equals 0 to infinity minus 1 raised by n z raised to power 2n plus 1 all over 2n plus 1 factorial. So if we divide, if we divide, if we divide, if we divide by z, we have that sine z all over z now is equal to summation from n equals 0 to infinity minus 1 raised to power n, z raised to power 2n all over 2n plus 1 factorial. You see, we had 2n plus 1 here because we divided by 1z, so this 1 is knocked off. So we have this z raised to power 2n over 2n factorial. So at this point now we can then say this series is valid. This series is valid for all z that is not equal to 0. But you notice that first of all, the series contains only non-negative powers, of z. They see only non-negative powers of z, as you can see there. Then it is well defined. It is well defined at z equals 0 by continuity. By continuity. So when you set z to 0, what happens? So z equals 0. So, I mean, everything will just go to 0, basically. So, then we can then compute. So we can compute the limit at z equals 0. That means that the limit as z approaches 0 for sine z over z. Of course, we can do L'Hopital's rule. That means limit as z equals 0. Because if you limit approach 0, so if you substitute directly, right, you're going to get sine 0 over 0, which is undefined. But by using L'Hopital's rule, you can still have sine, that's cos z over 1. So that means limits as z approaches 0 for cos z, and then that means you have cos 0, and that is equal to 1. So we see that the limit of sine z over z as z approaches 0 is equal to 1, like that. So we define f of 0 to be equal to 1. Thus, f of z can be extended to a power series, valid for all z, such that we have f of z equals summation from n equals 0 to infinity minus 1 raised to power n, z raised to power 2n, all over 2n plus 1 factorial. So this has infinite radius of convergence. Therefore, we can conclude, therefore, the function is entire after defining f of 0 to be equal to 1. And that's how that goes. So with this, we come to the end of that interesting video like that. I'll flash the questions again so you can remember to try your hands on them. So you have question 1 to 10 right here. Try them out. Then you have 11 to 20. I have done two of them for sure. I've done question question 6, of course, and question 16. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel, I thank you very much for that. And if you have not subscribed, the question is, what exactly are you waiting for? Go ahead, subscribe, and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you special privileges like getting to see some videos first before other people, or even seeing some videos exclusively, right? You could also request for PDF copies of my notes, so I can send some of my notes PDF copies. So if you want to really interact with those, you could also hang out with me online or physically if you're in the same geographical location at any point in time. As a member of the channel, we can always hang out like that. Ultimately, don't forget to comment, like, share, so that you can, so that other people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.